Hey everyone, Chris from FlipMath, and I'm going to take you through today's topic, which is on identifying types of series. I call it C2.5.2, and it's part of the sequences in series C2 module for C, although it's applicable to many other boards. Introduction. So in the last lesson, we examined arithmetic progressions, or if you want, arithmetic progressions are sequences where there's a common difference between the terms of the sequence. So, if there's a gap of 4 between the first and second term, there'll be a gap of 4 between the second and third term, etc. And we looked at four main aspects of the arithmetic progression. We looked at the first term was important. We looked at the common difference, like we've just discussed, was important. We looked at the number of terms. We used those together to get values for certain terms within an arithmetic progression by use of the nth term formula, u to the n. And we also looked at how do we get the sum of all the terms in a series, called S of n. In this lesson, we're examining the different types of series that there are then. The approach is still the same as you would in the other questions, or many of the other questions. You work out a few terms and make observations and decisions based on what you have. So, the types of series that we're going to try and differentiate between. So there's three main types. There's oscillating, there's convergent, and there's divergent. I'm going to take you through what each one of these both means, and also what they kind of look like, both in terms of numbers. And I like to always talk about things in terms of graphs, and what the graph looks like. So the first one we're going to look at is oscillating. And a sequence is described as oscillating if the terms repeat and stroke over alternate between getting bigger and smaller. So, examples of that would be like 1 minus 1, 1 minus 1, 1 minus 1. So that team goes between positive and negative, positive and negative, positive and negative. Similarly, if I look at 753, 579, 753, 579, you can see that is going to constantly go up and down. It never goes into the minuses, but it goes down and up and down and up. And those graphs, some ways look like that. There's a sine graph, for instance, where it goes up and down and up and down and up and down. It's basically just going to repeat all the time, and it's oscillating. If you imagine like a metronome, if you've ever seen one of those go back and forward, bong, hits one side to the other, one side to the other, constantly. It never goes beyond the scale of where it is. It just kind of oscillates between those 2 points. And that's an oscillating sequence. And a convergent series is a sequence that gets closer and closer to a certain value. And again, it helps if you graph it, but if I give you an example of that sequence, something like 7, 5, 4, 3.5, 3.25, 3.125. As you can see, the gap between the first and the second is 2, then it becomes 1, then it becomes a half, then it becomes a quarter, then it becomes an eighth, etc. as you go down. So it's constantly, the gap between those terms is getting smaller and smaller. And that's really what defines it. You can see that this sequence is heading towards 3. We'll call that a limit. And the graph of that looks something like this. So we would have a point, the points plotted 1, 2, 3, 4, 5, 6, and you see it's kind of heading there. And in many of the examples we've done that when we were doing graphing and C1, etc., we talked about that limit being an asymptote. It never actually quite gets there. There's always just a wee bit off it. It was an asymptote. That's what we're talking about. That's the type of convergence series. So that's what that graph looks like when we're talking about that. And the last type is divergent. And you can use divergent to really talk about any other series that you have. But in general, it's neither convergent or oscillating, so it must be divergent. The terms may be getting further apart or staying the same distance apart, but not oscillating. So examples would be 1, 2, 4, 8, 16, 32. You can see the gap between those is getting bigger. So the difference between them is divergent if you want. So the gap between the first two is 1, then the gap is 2, 4, etc. And then with something like minus 7, minus 5, minus 3, minus 1, 1, 3, 5. It does go from negative to positive, but it doesn't switch between the two of them. If it did, it was oscillating. This one isn't. There's just a constant rise of 2. And if I show you what those two graphs look like, You can see the one on the orange is this -7, -5, -3, etc. And the one above is the 124. The one in blue is the 124, 8, 16, 32. So they're the three different types that you have, and I hope you've made some notes to that effect, because we're going to look at three examples. The general approach, like I said before, was work at the first few terms and then examine for patterns. So the first example, and we're going to take the same approach for all of these. We're going to work at the first four terms of the sequence and decide whether it's oscillating, divergent, or convergent, and if it's converging, we're going to state its limit or the value that it's tending towards. So the first one we're going to look at is an nth term, or in this case an rth term, of u to the r equals 3 plus r squared. And we're going to work out the first four terms. So we're going to stick in u to the 1 to be, replace the r with the 1, so we get 3 plus 1 squared, which is 4. Second term is 3 plus 2 squared, replacing the r with 2. That'll be 3 plus 4, which is 7. That's a gap of 3. U to 3 is 3 plus 3 squared, which is 3 plus 9, which is 12. So with a gap of 3, we've now have a gap of 5. And the fourth term is 3 plus 16, which is 19, which is now a gap of 7. And you ask yourself, is it oscillating? Well, it's not bouncing back and forth between getting bigger, smaller, or positive and negative. So it's not. Is the gap between the numbers getting smaller? Well, it goes 3, 5, 7. So that's not true either. In fact, it's doing the opposite. And when the gap between the numbers is getting bigger, it's divergent. And that's our answer. That is a diverging series. And that's all you need to say. We'll look at our second example. And again, we're going to work out the first four terms and state then whether it's oscillating, divergent, or convergent. If it's convergent, state its limit as before. And the nth term that we were given is x to the r equals 2 cos 180 times r. And just to be clear, that's in degrees. So we're going to put r equal to 1. So it becomes 2 cos 180 times 1. 180 times 1 is 180. So we're going to get 2 cos 180. And if you pop that in your calculator, you'll find that that value is -2. If I do 2 cos 180 times 2, pop that in your calculator, do your 180 times 2 to give you 360 first. And then do 2 cos 360, you'll find that that's +2. When I do it for 3 and 4, you'll see that it goes -2 plus 2. Once you've got that done, you can decide whether it's oscillating, convergent, or divergent. Well, if you look at it, it goes -2 plus 2, -2 plus 2. You could draw that in a little graph for yourself, but you'll see that it bounces back and forward between positive and negative, and therefore that makes it oscillating. And that is an oscillating series, and many trig functions are oscillating series. Third and last example is we're going to work at the first four terms, decide whether it's oscillating, divergent, or convergent, and if converging, state its limit. Our nth term is u to the r equals 2 minus 9 over 3 to the r. Stick in r equal to 1. I'll have 2 minus 9 over 3 to the power of 1, which will be 2 minus 3, which is -1. Second term, I'll replace the r with 2. That's 2 minus 9 over 3 squared, which is 2 minus 9 over 9, which is 2 minus 1, which is 1. When we replace the r with 3, again, you can pop that into your calculator, but you'll get that that's 5 over 3, and that's 17 over 9 when we replace it with 4. You will see that the gap between them is getting smaller and smaller. So the gap between here and here is 2, the gap between here and here is 2/3, etc., etc. And you can actually see by looking at this, as r gets bigger, this fraction, or the number in the bottom, is going to be bigger and bigger. The number at the top still says the same, so we could have 9 over 14 million here, which is effectively 0. And you can see that this will tend towards 2. You can see this getting closer and closer to 2. And for that reason, we can say that it is convergent. The gap between the terms is getting smaller and smaller. And I can make a guess or a stab that the limit is equal to 2. We look more in class or further on at how we can basically make sure that as the number gets really big, this part here becomes 0. Effectively comes a smaller and smaller fraction, so that then this will, what they say, tend towards 2. And if you graphed it, you would see very much the same thing. So it's time for some practice. You may even spot some patterns. So you can go on the Moodle or on any of the exercises on the site and work out the first couple of terms and decide whether it's oscillating, convergent, or divergent. And if it's convergent, state its limits. Thank you very much for watching, and I'll catch you next time.